Hello friends. So in the mass spectroscopy topic, till now we have studied ionization and fragmentation of different classes of organic compounds such as alkane, alkene and aromatic hydrocarbon. In this lecture we will discuss the ionization and fragmentation in case of alcohols. We know that alcohols are nothing but organic hydroxy compound, and there are three types of alcohols: primary, secondary and tertiary. I will write the example of each class of organic compound. This is primary alcohol CH3 CH2 CH2OH, primary alcohol 1 propanol. Then this one is secondary alcohol. One of the hydrogen from this is replaced by alkyl group, and therefore it is a secondary alcohol. And finally, the example of tertiary alcohol is like this. Here there is a carbon and CH3, CH3. You can write C2H5, C3H7, any alkyl group. So for our convenience and for better understand, I have put the examples of primary, secondary and tertiary alcohol. Now look at the structures of primary, secondary and tertiary alcohol. There is a presence of OH group and OH group. The general formula for alcohol is ROH, that we have known. And this oxygen has lone pairs of electron. How many? Two lone pair of electron. Therefore, there are 4 electrons. And these 4 electrons, they are not participating in the chemical bonding. That's why they are also known as non-bonding electron. Non-bonding electron. Now, in the molecular ion formation, we have studied the ease of formation of molecular ion. Molecular ion means M radical cation. Ease of formation is observed like this: non-bonding electron greater than pi electron than sigma electron. What does it means? The non-bonding electrons are easily lost as compared to pi electrons, as compared to sigma electron. Therefore, as there is a presence of non-bonding electron in case of alcohols, the molecular ions are formed by the loss of these electrons. So, in the ionization process, there is a loss of non-bonding electron. Okay. So, next point is ionization. So, the picture is very much clear. Alcohol contains non-bonding electron as well as sigma electrons. If there is unsaturation, then it may contains pi electron, but the ease of formation is non-bonding greater than pi than sigma. It means that in case of alcohol, non-bonding electrons are lost easily during the ionization process. So in the ionization process, what happens? Alcohol, when it is bombarded with high energy electron, then one of the electron from the oxygen has how many electrons? 4 electrons. Out of the 4 electron, 1 electron is lost during the ionization process, and it will changes like this. Oxygen contains positive charge. This is the single electron and these are the lone pair. So out of the 4 electron, 1 electron is lost during the ionization process and we get molecular ion of alcohol. So whatever may be the structure of alcohol, we can get this type of molecular ion in which the positive charge resides on alcohol. This is the positive charge which is present on the OH, that is oxygen. Okay, whatever may be the structure of alcohol. Now, take 1 propanol CH3 CH2 CH2OH. What will happen? These are the 4 non-bonding electrons. When it is bombarded with high energy electron beam, then it will form the molecular ion like this CH2, then OH, but oxygen has positive charge, single electron, and this is a lone pair of electron. Then this is the molecular ion of one propanol. In case of secondary alcohol, again we get the molecular ion CH3, CH2, CH, CH3. There is a OH having lone pair of electron. When it is bombarded with high energy electron, we get the molecular ion like this. OH, oxygen contains positive charge, single electrons, and lone pair of electron. In this way, in case of primary as well as secondary alcohol, we get the molecular ion formation. In case of tertiary alcohol, there is also formation of molecular ion by losing one of the non-bonding electron from the oxygen, and the positive charge resides on the oxygen after the ionization. Then, what is the stability of a molecular ion? That we are going to discuss now. Stability of molecular ion. The stability of molecular ion, we know that the stability of molecular ion depends upon the structure. Depends upon the structure. It means that it depends upon the presence of unsaturation or pi electron system. If there is a presence of unsaturation or any pi electron or aromatic ring near to the cation, then that molecular ion is more stable. If you look the structures of molecular ion here in primary alcohol, then here in secondary alcohol, then it is found that there is an absence of pi electron system here and here. The pi system is absent. Pi system is absent or unsaturation is absent. That's why the stability of the molecular ion is very much less. And in case of tertiary alcohols, the example of tertiary alcohols that we have taken initially, this one CH3, CH3, then there is a OH here electrons. The characteristics of this tertiary alcohol is that it undergoes easily elimination reaction or dehydration reaction, and it forms this type of compound CH double bond C CH3 CH3. So these alcohols are very unstable one. They undergo easily dehydration. This OH group and hydrogen from the CH2, they will eliminated as a H2O, and it generates alkene when they heated. So that's why in case of tertiary alcohols, whatever the molecular ions that are formed, they are unstable one. Okay. So in molecular ions are unstable. And in case of primary alcohol and secondary alcohol, the molecular ion stability is less. That's why we get in case of alcohols either very weak or undetectable, very weak or undetectable molecular ion peak in mass spectrum. But if I take the example of aromatic alcohols, in case of aromatic alcohols, I will write the example of aromatic alcohol like this. This is the example. This is the benzene ring. Then here there is a CH2 and it is OH group. On oxygen, there is a lone pair of electron. This is nothing but the benzyl alcohol. and when it undergoes ionization, it forms benzene ring remains as it is, then CH2, then OH. Oxygen contains positive charge, lone pair of electrons. This is the molecular ion of aromatic alcohol, that is benzyl alcohol. Now, in this structure, this is the aromatic ring which is attached to CH2OH. That's why the molecular ion of aromatic alcohol is stable one. Why it is stable? Because there is a presence of aromatic ring. Aromatic ring is there. That's why it is stabilizing the molecular ion, and therefore in case of aromatic alcohol we get a prominent peaks. Why? Because there is a presence of pi electron system or aromatic ring, and that stabilizes the molecular ion, and therefore in case of aromatic alcohols we get a prominent molecular ion peak. Prominent means they are having more intensity. They are having more intensity. Molecular ion peak. So these are the characteristics of molecular ion peak in case of alcohols. Aliphatic alcohols, very weak or undetectable molecular ion peak, whereas aromatic alcohol shows prominent ion peak. So I hope that you have carefully studied and you have understand the ionization process in case of alcohols. Now we will turn towards the fragmentation patterns in case of alcohol, how the alcohols are fragmented, how the bond breaking process occurs during the fragmentation, that we are going to study in this point. So in case of alcohols, there are three types of fragmentation patterns. First one is alpha cleavage, second one is dehydration, and third one is rearrangement. So first of all, we will see the alpha cleavage. Now we have to know what is meant by alpha cleavage. Alpha cleavage is nothing but the cleavage of carbon-carbon bond next to oxygen. You have to keep in mind that carbon-carbon bond next to oxygen, if it is broken down, then that is called as alpha cleavage. It can be better understood by taking the example CH3, CH2, CH2OH. This is one propanol. When it undergoes ionization, it will form molecular ion CH3, CH2, CH2OH, positive charge, single electron, and lone pair of electrons. Now, look at the structure of molecular ion of one propanol. In case of one propanol, this is the oxygen, and next carbon-carbon bond is this. This carbon-carbon bond is next to the oxygen. If this bond is broken down, then it is called as alpha cleavage. And how this bond is going to break? It is broken down via homolytic fission. So carbon-carbon bond which is broken down by homolytic fission. We have to keep in mind bond breaking process occurs through homolytic fission. What is meant by homolytic fission? It means that from this bond one electron is transferred to this carbon and second electron is transferred to this carbon. Therefore, the fission occurs or breaking occurs in such a way that two atoms, they are getting one electron each, and that is known as homolytic fission. Same, both the atoms get same electrons, that is one electron to each. Now, in case of one propanol, how this homolytic fission occurs, that we are going to study. Here, alpha cleavage occurs in such a way that one of the electron is transferred from this bond to this carbon, and second electron is transferred from this bond to here, this bond. And this is the single electron which is present on the oxygen is transferred from this to this. Now, this bond is going to break down and we get CH3CH2 radical plus remaining structure here is CH2 then OH and on oxygen there is a positive charge and from this oxygen one electron is transferred here. From this bond, one electron is transferred here. Therefore, there are two electrons. Two electrons means one bond. Therefore, in carbon and oxygen, there is a formation of double bond due to the homolytic fission. And in this way, we get one radical and this is a cation. So in this way, in case of one propanol, we observe ionization and in ionization we get the molecular ion having M by Z value about 60. Here you can find out the mass is even but there is a presence of odd electron. Here is a one electron then here are two electrons. Therefore it is even mass and odd electron pairs. So after ionization we get the molecular ion having M by Z value 60, even mass and odd electron. But after the alpha cleavage what we are getting here, there is a radical and here it is a cation in which positive charge is reside on oxygen. But the M by Z value of this cation is about 31. If you calculate, it means that it is odd mass species, but the electrons on this species are 2. That is lone pair of electrons. Therefore, even electron. So after alpha cleavage, we get the cation having M by Z value 31. Generally, the primary alcohols gave a cation having M by Z value 31. After the alpha cleavage, it is characteristic peak observed at 31. Now, we will turn towards the secondary alcohol. Example is CH3, CH2, CH2, then CH, here there is OH and CH3. That is 2-pentanol. 2-pentanol. First step, ionization. In ionization, it will form the molecular ion CH2. I will write OH below, in which there is oxygen and having positive charge and 3 electrons. Once again, it is odd electron pairs because there are 3 electrons, and if you calculate the M by Z value of this species or this molecular ion, it is found to be 88. That is even mass. Now, in case of secondary alcohol, what we are getting here, there is a possibility of 2 alpha cleavages. 2 alpha cleavages because next to this oxygen there are 2 carbon-carbon bond. This is first carbon-carbon bond and this is second carbon-carbon bond. Therefore, there is a possibility of 2 alpha cleavages here also and here also. Therefore, in secondary alcohol, we can get 2 alpha cleavages. Now, from these 2 alpha cleavages, which one is preferred one, that we are going to see. Okay. So, out of the 2 alpha cleavages, we get one preferred and that we are going to study. So, I can write here this molecular ion having M by Z value 88, it will undergo alpha cleavage. First of all, we take this root and I will write here alpha 1 and this is alpha 2. So alpha 1 and this is alpha 2. So first, suppose this bond is going to break and one electron is shifted from this bond to this carbon and second electron is shifted here. Then we get one radical and one cation like this. One radical, that is CH3, CH2, CH2 radical, plus cation. First of all, I will write CH, then OH, but electron is shifted from alpha cleavages. Therefore, here there is a double bond and oxygen contains positive charge and there are two electrons, that is lone pair of electron, and here there is a CH3. Now this is the radical and this is the cation, and M by Z value of this cation is 45. Now here look, M by Z value is 88, it is even mass odd electron, but here M by Z value is 45, that means it is even electron and odd mass species. This is first root. Then second possibility, that is alpha 2. According to alpha 2, this bond is going to break and we get CH3 radical and the remaining part as a cation. So I will write here CH3 radical plus CH double bond OH, positive charge, two electrons, that is lone pair of electrons, then CH2, CH2, CH3. M by Z value, if you calculate, it will found to be 73. Once again, it is even electron because two electrons are there on oxygen and odd mass. Now, in the fragmentation rule, it is clear that the radicals having or larger alkyl radicals are formed in case of fragmentation rather than smaller alkyl radical. So out of the alpha 1 and alpha 2, here is propyl radical. Here is propyl radical, whereas in alpha 2 it is methyl radical. Out of the two radical, this one is larger one, that is propyl radical is larger one and this is smaller one. That's why the alpha 1 cleavage is preferred one or it is favorable because in this case there is a formation of larger radical. So we get the M by Z value at 45. This peak is prominent one in case of secondary alcohol. Second pattern is dehydration. So dehydration is nothing but the removal of water molecule, that is H2O. Alcohol contains already hydroxyl group. Therefore, that hydroxyl group and one of the hydrogen from other carbon, they may combine to form water molecule and it is eliminated in the fragmentation process. Consider the example of once again secondary alcohol CH3, CH2, CH, here OH and here CH3. So after ionization, what will happen? We get CH3, CH2, here CHOH and CH3. Now on oxygen, there is a positive charge, single electron and lone pair of electron. Here there are two lone pair of electron. This is the ionization process occurring in 2-butanol. Butanol. This is molecular ion. Now, in dehydration process, what happens? The hydrogen from this carbon, is removed. How? I will write the structure like this: CH3, CH, one hydrogen I can write here, then again CH OH, positive charge CH3. Similar structure I have written, but one hydrogen is written above the carbons. So now what happens in the dehydration process? This hydrogen is going here and it will combine with the OH group, and one electron is shifted here, and what we are getting, look at this point, one electron is shifted here, one electron is shifted there. That's why this changes to CH3, then here is a CH, and on that carbon single electron, then here CH, here CH3. Now oxygen, this oxygen is attached to one hydrogen, and this hydrogen is shifted from this carbon to this oxygen, therefore one hydrogen is shifted. Now there is a positive charge. In next step, what happens, this H2O is removed and we get CH3 CH radical, CH CH3, and in this carbon there is a positive charge. In this way dehydration in case of 2-butanol occurs and we get the ions, and M by Z value of these ions is M minus 18. M minus 18. Why M minus 18? It is due to the loss of water molecule having value 8. Water molecule has value 18, that's why whatever the M by Z value of the molecular ion, minus 18 is nothing but the M by Z value of this ion. In this way the dehydration in case of alcohol occurs. This is the second route of fragmentation. Now we will turn towards the rearrangement that is occurring in case of alcohols. So last pattern observed in case of alcohol is rearrangement. So I will write here rearrangement. Rearrangement. Simple. It is so much simple, but you have to identify the gamma hydrogen. Which hydrogen? Gamma hydrogen. If any alkyl molecule contains gamma hydrogen, then there is a possibility of rearrangement. Then there is a possibility of rearrangement. How it is going to rearrange? Okay, let us consider the example of this type of molecule, that is CH3, then CH2, then CH2, then CHOH, CH3. Name is 2-pentanol. 2-pentanol. Now you can assign this carbon as a alpha carbon, this carbon as a beta carbon, and this carbon as a gamma carbon. Therefore, on the gamma carbon, there are 3 gamma hydrogens. So, rearrangement is possible. How you can see here? First step, ionization, CH3, CH2, then CH2, CH OH, oxygen contains positive charge, and CH3. M by Z value of 2-pentanol, we know that it is 88. Okay. Now, after ionization, we get the rearrangement of gamma hydrogen. For that purpose, we have to write this structure like this. I will write here only CH2, then here CH2, here also CH2, then I will write here CH and CH3, here OH, positive charge, then single electron and lone pair of electron. And one hydrogen I will write like this. Now you can look at the structure CH3, CH2, CH2, CHOS, CH3, but it is written in such a way that it looks like a six-membered ring, and you can easily see the shifting of gamma hydrogen from carbon to oxygen. How? Okay. Rearrangement occurs in such a way that this bond is going to break and one electron is shifted here, and that electron is combined with this electron. Then second electron is shifted to this bond. Now what happens? This bond, that is alpha carbon and beta carbon, the bond between alpha and beta is going to break here. After breaking, one electron is shifted from this bond to this bond, and second electron is shifted to this carbon. So in this way rearrangement occurs. The hydrogen is shifted from this carbon to oxygen. This electron is shifted from this carbon to this, okay, and alpha beta bond is broken. So here we can write shifting of hydrogen or rearrangement of hydrogen with breaking of alpha beta carbon carbon bond, okay, and we get, I will start from this side. I will write CH2 double bond CH2. Why double bond? Because electrons shifted from this bond to this bond. There are two electrons. That's why there is a double bond formation. Then plus CH2 radical. Which carbon? This carbon. Okay, CH2 radical. Then there is a single bond CH. Then CH3. Now on this carbon there is a presence of OH, and hydrogen is shifted from this carbon to OH. That's why this OH is changed into this one H2O, and oxygen has positive charge. What happens? This water molecule again it is removed as a H2O, and we get CH3, then CH positive, and then CH2 radical. In this way we get the rearrangement reaction in case of alcohols having a gamma hydrogen and M by Z value, peak at M by Z value 42 is observed. It is due to the rearrangement of gamma hydrogen in case of alcohols. So in this way there are three patterns of fragmentation that are observed in case of alcohol. First is alpha cleavage, in which larger alkyl radical pattern is preferred one. Second one is dehydration, water molecule is removed, and third one is rearrangement, in which there should be a presence of gamma hydrogen. So all this pattern that we have learned in case of alcohol, that can be repeated by using some spectrum. I will show you a spectrum of 1-propanol. You can find here, this is a spectrum of 1-propanol. In that spectrum, this is the peak where M by Z value is 60. Okay, this is the molecular ion peak. Molecular ion peak, that is M peak, because 1-propanol has formula CH3 CH2 CH2OH, and that's why molecular ion peak is observed at M by Z value 60. Intensity is very weak. Now in case of 1-propanol, we know that there is a alpha cleavage, and after alpha cleavage we are getting the peak at 31. So this is the peak having M by Z value 31. It is due to the alpha cleavage, and we get the cation like this CH2 double bond OH that we have seen in the earlier discussion. M by Z value is 31. as compared to the intensity of molecular ion peak. This intensity is very much high. That's why it is a base peak. So in case of primary alcohol, base peak is observed at 31. So after alpha cleavage, we are getting CH2 double bond OH positive charge. This is the peak. It is a characteristic peak at 31 observed in case of primary alcohol. And there are number of peaks observed beyond 31. Okay. So these are the two characteristic peaks observed in case of 1 propanol. Okay. Then second example that we are going to take is 2-pentanol. Carefully observe the spectra of 2-pentanol. Structure of 2-pentanol that we are having CH2, 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 then CHOH and CH3. After ionization, it will form the cation like this, that is molecular ion, and molecular ion peak is observed at M by Z 88. But if you see the spectra of 2-pentanol at 88, the peaks are absent. Okay, so in the earlier discussion, in the stability of molecular ion of alcohol, we have seen that either very weak or undetectable peaks are observed. So here 88 peak is absent one. So it is undetectable one. But after alpha cleavage, we can get the peaks at either 45 or 73, out of which the peak at 45 is prominent one, and at 73 it is less prominent or it is minor peak. So this is the peak having M by Z value 73. In this peak, the radical CH3 radical is formed and corresponding cation is formed. Okay, whereas in this alpha cleavage, there is a formation of CH3, CH2, CH2 radical and corresponding cation having M by Z value 45. So out of which this radical is larger one. Therefore, the alpha cleavage which forms the cation having M by Z value 45 is favorable, and the peak at M by Z 45 is this one, and it is having higher intensity, therefore it is also a base peak. It is also a base peak. Now this 2-pentanol also contains alpha hydrogen, gamma hydrogen, and due to the gamma hydrogen it will show rearrangement, and we get peak at M by Z value 42. This peak, it is due to the rearrangement 40. In this way, we can see the spectrum of 1-propanol as well as 2-pentanol and different types of fragmentation patterns that are occurring in the corresponding alcohols. We will revise what we have learned in this lecture. So first of all, we have studied the ionization of alcohols, in which we have studied the molecular ion stability. The molecular ion peaks are very weak or undetectable. They are very weak in case of primary and secondary alcohol, whereas they are undetectable in tertiary alcohol. Whereas in case of aromatic alcohol, they shows prominent molecular ion peak, that is intensity is high. It is due to the presence of aromatic ring near to the oxygen. Then after ionization, we have studied the fragmentation pattern, in which first pattern is alpha cleavage, a breaking of carbon-carbon bond which is next to oxygen, and it leads to the formation of larger alkyl radical when there is a possibility of 2 or more alpha cleavages. Larger alkyl radical is favorable. In primary alcohol,
Generally, it will shows peak at M bar Z31. It is characteristic peak in primary alcohol. Whereas in case of secondary alcohol, we get the peak at either at 45, 59 or 73. It depends upon the what kind of alkyl chain is present in the secondary alcohol. Second pattern is dehydration, in which water molecule is removed, therefore we get M minus 18 peak. And last fragmentation pattern is rearrangement, in which gamma hydrogen is transferred from carbon to the oxygen with the removal of water and smaller alkene, and it will form the corresponding cation. In 1 pentanol, the peak observed at M by Z42, it is due to the rearrangement. In this way, we have studied the ionization and fragmentation patterns in alcohol.